Welcome to VLSI technology lecture. So in the last lecture, we have seen the various wafer cleaning technology. And now today we are going to see another way, we have today's topic. We are going to discuss about the thin film, growth of the thin film onto our wafers. Okay, so we have to see how various thin films, because while NMOS fabrication, I have already explained, while fabricating any transistor, either it is NMOS, PMOS transistor, it may be a BiCMOS, BJT. Okay, we need to grow multiple layers. Okay, it may be a monocrystalline layer or it can be a polycrystalline layer. So we have to grow different type of layers. It may be a silicon, means it may be a semiconductor material, okay, or it may be a dielectric material, it may be a metals, it may be a various different type of thin film we need to deposit onto the particular wafers. So either it is a wafer or it is already containing a particular layer. So we need to grow different type of materials. Okay, a very thin layer of different type of material we need to grow. So basically, when we talk about the thin film, basically it must be having a thickness of the order of nanometers. It may be like 1 nanometer to it may be 10 nanometers, 20 nanometers, or maybe more, as per the requirement. Okay. So basically, we need to grow this type of different layers onto the particular material. So if we want to deposit a particular thin film onto a wafer, you can say either it is a substrate or it may containing a particular layer onto the substrate, and onto that we want to deposit a particular layer. Then to deposit these layers, basically we are having a two broad category of deposition technique. Okay. So the first deposition technique that is known as the chemical vapor deposition. Okay, which is in the short form it is called as CVD technique. Okay, which is very popular, chemical vapor deposition. And the second one is called as the physical vapor deposition. Okay, so this is the broader classification by which we can deposit our any material onto the particular substrate. So now you can see in the chemical vapor deposition, basically what happens is whatever the layer that we want to grow onto the wafers, first of all, we have to take the source of that particular material, and that source may be in the form of gases, it may be in the form of vapors form, or it may be a liquid form. Okay, it may be in the form of beams also. Okay, we can take the solid material and then we have to hit through a very energetic particles. Okay, and then a certain beam of that particular material will come out and then it will get deposited to the particular layer. So basically what happens is in the chemical vapor deposition, what we need to have is we need to have the reactant gases. Okay, the source will be a reactant gases or it may be a reactant liquid. So first of all, it need to be transported to a particular chamber in which this growth will take place. So when it is going inside the chamber, okay, it will have a particular chemical reaction onto the wafer surface. Okay, so it will make a reaction, and after the reaction, a certain byproduct will be formed. Fine. So this is our chemical vapor deposition. What we mean to say that. Okay. So in the chemical vapor deposition, as I have already written here, that the reactant gases introduced in a chamber. Chemical reaction occur on a surface, wafer surface, leading to the deposition of a solid film. Okay. So if we compare the chemical vapor deposition with respect to the physical vapor deposition, you can see this in the physical vapor deposition, there is no chemical reactions. Okay. So there will be no reaction take place. Fine. So only the vapors of the constituent material will be sent inside a chamber, and after the condensation, it will get deposited over the particular layer. Okay. So we have a different examples for in the case of chemical vapor deposition. We can see chemical vapor deposition can take place at atmospheric pressure. Okay, so that is known as the APCVD technique, atmospheric pressure chemical vapor deposition. Similarly, it can also take place at low pressure. Okay, so it will be called as the LPCVD technique, low pressure chemical vapor deposition. Similarly, we can also have a CVD technique which will be supported by plasma enhanced. Okay, it is a plasma enhanced chemical vapor deposition technique. Okay, so we can have the plasma enhanced chambers in which we can do the means deposition of various layers. So we can see the chemical vapor deposition is a very popular technique. Okay, CVD technique is a very popular technique, and basically the CVD is actually suitable for dielectrics, for the deposition of the dielectrics, various dielectrics and the silicon layers. Okay, so if we want to grow a particular silicon layer or a dielectric, then we have to go for the CVD technique. But in the case of like metals, if we want to grow the metals, okay, or any alloys, okay, the same thing cannot be possible by CVD technique. Okay, this CVD technique will not be suitable for metal deposition. So for these purposes, we have to go for the physical vapor deposition processes. Okay, in which we are having a different technique again, like evaporation method, sputter deposition. Okay, so this will be used for your metal deposition or alloy deposition. So basically what we are saying that the dielectric and semiconductors, metals and polymers, these are the different things that we want to grow during the IC fabrication. Okay, so that we want to grow, and these are the two different techniques by which we can grow these particular layers. Now question comes, basically in the chemical vapor deposition, what we are saying, it is a deposition technique. Okay, so when we are saying it is a deposition technique, deposition can be a monocrystalline layer and it can be a polycrystalline layer. Okay, you can grow both the types of layers. Fine. So there is one category. Actually, this deposition or chemical vapor deposition is a subcategory of the epitaxy. Okay, so there is one method which is called as, or you can say the epitaxy is one of the subcategory of the chemical vapor deposition. We can say, because in the epitaxy, what we do is, in the epitaxy we can grow a monocrystalline layer. Okay, it is just containing a single crystal structure. So when we have a particular wafer, and then onto the wafer we want to grow a certain layer. Okay, when in the wafer we have, or a substrate we have, and onto that substrate we want to grow a particular layer, and that layer should be a monocrystalline layer. If it is a monocrystalline layer, then if we follow a chemical vapor deposition, then it is also known as epitaxy method. So the another name that the CVD technique got is epitaxy. Okay, when we are growing a monocrystalline layer. But whenever it is a polycrystalline layer, we can say it is a CVD technique simply. No issues. Fine. So we have to look at in the today's discussion, what are the different techniques for epitaxial method, epitaxial layer, how to grow epitaxial layer. So first of all, what we are saying that you must remember these things, okay? Because CVD technique will be used for the dielectrics and silicon deposition, that you remember. Silicon is a semiconductor material, right? And PVD technique will be used for your metals or alloys, that you have to remember, right? So in the discussion, we have to talk about the epitaxy. So first of all, what we mean by saying the epitaxy, okay? So first of all, the epitaxy will be used for depositing a monocrystalline film, okay, a very thin film that will be deposited over a substrate, okay. So this is a Greek word. So basically, AP means above and taxis means the ordered. So what we have to do is we have to grow a monocrystalline layer, or you can say a very ordered layer, onto or above a particular substrate. Okay, above a particular substrate, we have to grow a particular ordered layer. Fine. So to grow this type of epitaxial layer, we can have our sources in the form of gaseous form, or it can be a liquid form. Okay. It can also be in the form of solid, and later on it has to be converted into a beam. Okay. So in the molecular beam epitaxy, what we have is we are taking the solid sources, and that these solid sources will be heated by energetic particle, and then a beam will be come out. Okay. So we can also take the solid sources, or you can say beam will be the sources for epitaxial layer growth. So these are the different sources. Then basically whatever we want to grow, let us say we grow onto a particular substrate. Then whatever be the substrate possessing the properties, okay, it is having a certain like orientation, you can say a particular lattice constant, okay. So whatever properties that our substrate is having, okay, some of the properties will be followed by your epitaxial layer also. Okay, you just remember, I'm not saying that all the properties of the substrate is going to be converted into the epitaxy, but some of the property, like if it is a monocrystalline layer, then again we have to grow a monocrystal layer onto that. Okay, and then it will be following a certain property of this, and it will be acting like a seed crystal. Okay, and then the temperature and the substrate determines the physical structure of the deposited film. Okay. Whatever we are going to deposit, so whatever be the substrate, what kind of substrate it is, and what temperature we are doing this particular epitaxy method, that will be going to decide the what kind of layer we are going to deposit. So we need to understand what is the need of this epitaxy, okay, why we are going for growing a particular layer, why it is needed. Okay, so first of all, you can understand that we have a substrate, and sometimes we know that the substrate we got from substrate, or you can say we got the wafers from the ingot. Okay, so during the ingot formation or the pulling of the crystal, what we do is we adding a certain type of impurities into the melt to get a particular type of substrate. Okay, so this will be either p doped or n doped. Okay, this is n doped or p doped, whatever it can be, and the amount of doping can be controlled at that time only. Okay, so basically, when once you have already fabricated a substrate, later on you cannot change the property of the substrate. Okay, it will have a certain resistivity, it will have a certain amount of dopant that will decide the resistivity, it will have a certain amount of you can say it is having a particular crystal orientation. Okay, so if your device requires some other parameters, okay, if the parameter of the substrate is not suitable uh, for fabricating your device, either you can go for a fabricating a new substrate, or what we can do is we can grow a layer onto the substrate of desired specification. Okay, so whatever your specification that you want, I want a particular layer onto the substrate onto which we want to make a circuit. Okay, so what we can do is either we can go for making a new substrate, making a complete new wafer, so that that wafer can be directly used for making the circuit, or what we can do is we can take a already available wafer, and then we can do the modification, and we can grow a particular layer onto that, that will have our desired specifications. Okay, sometimes the wafers or the substrate that we get is not so pure. Okay, and that's why what we need a very pure layer in which we want to make our circuits, okay, or make our devices. So basically what we have said till now is the epitaxy is actually a way in which we are growing a monocrystalline layer. Okay, so first of all, we have to grow a monocrystal layer. So we are having a particular wafer crystal onto which we have to grow a AP film. Okay, epitaxial layer we have to grow, and that will be a monocrystalline film. Okay. So if it is a polycrystalline film, because we can grow also like SiO2, we can also grow over a particular substrate, then it is readily known as deposition. Okay, we are depositing a layer. It is not called as the epitaxy. So that you remember, right? So that will be your polysilicon film growth, can be also called as the deposition of the layers. Fine. So now, so what we have said. So first you try to understand the types of epitaxy. Okay, what are the types? So basically here the types I have defined in the different way, like in this case we have defined the type what is the substrate material and what is the material that we want to deposit onto the substrate. So for example, if the substrate and the material that we want to deposit onto the substrate both are same, then obviously it will have a lattice matching. Okay, it will have a lattice matching. So both materials are same. So when these two materials are same, the epitaxial layer as well as the substrate, it is called as the homoepitaxy. Okay, and whenever we are growing a particular layer onto the substrate, okay, which is not same as the substrate, okay, if the AP layer is different from the substrate, then obviously it may or may not be matching, it will not have the same lattice constant, okay, and therefore what happens is there may be a chances that the layer that we are going to uh, deposit onto this particular substrate, because these two materials are different, okay, either it will form a strained layer, okay, because of the lattice mismatch, or it may be having a relaxed layer, or it is a compressed layer, okay. So that type of layer can be formed. So basically what you have to understand is there will be a homoepitaxy, or it can be a heteroepitaxy. Okay. In the homoepitaxy, we have the same epitaxial, the material of the epitaxial layer and the substrate both are same. And in the heteroepitaxy, both these materials will be different. Okay. So if it is different, obviously it is called as the heteroepitaxy. And within the heteroepitaxy, we are having a strained layer, or it may be a relaxed layer. You can say it is a compressed layer. Okay. So that type of layers can be formed. So now, whenever we want to talk about the homoepitaxy, as I said, sometimes whatever the substrate we are having, that substrate is not containing the desired specification in the form of either you can say in the terms of its purity, you can say, or in terms of its doping profile, you can say, okay, in terms of its orientation, you can say, okay. So if it is not having the property that you want, that time we can go for the homoepitaxy, okay, and we can grow another layer, okay, and then we can control its parameters, okay, whatever parameters that you want, that we can control. Similarly, the heteroepitaxy is basically used for the band gap engineering, okay. So right now we are not focusing on to this, okay, but there is a band engineering occasion in which we have to grow a heterostructures, okay. So that heterostructures will be used for various optoelectronic applications, okay. So there we can use the heteroepitaxis. So now we have to basically focus on to this one, okay. So now we can see what are the advantages of the epitaxy. So basically, as I said, we can make this monocrystalline layer very high purity, of very high purity. Silicon film can be grown. Okay, we can do it fine. And similarly, we can control the thickness, like you can see the large interval of thickness, doping profile, band gap. Okay, everything we can control. Okay, there could be some artificial semiconductor structure could have been created. It is already created and they have got the Nobel Prize, like HBTs, okay, heterojunction bipolar junction transistors, okay. And then we are having the HEMT, high electron mobility transistors, which is based on the two-dimensional electron gases, okay. So because of this epitaxy method, we are able to uh, get this mobile devices, okay. So these are the some advantages, okay. We can control the properties of the layers. We can have a very excellent control over the thickness, having excellent control over the doping profiles, okay. We can control the band gaps, okay, and thereby the physical characteristics of the devices, okay. So what are the various applications you can see? So basically we are saying it is engineered wafers, okay. So what we are doing is, so we have already got a substrate, and onto the substrate, what we can do is we can further change the properties of the substrate, okay, by growing a new layer, so that we can get the specification of our desire, okay, whatever we want, okay. So as per our requirement, we can change the properties of the our layers. You can say the substrate. So we can get the flat layer onto the top, those who are having a less ideal silicon substrate, okay, those substrate which is not having the properties, or not containing the properties that we want, okay. So on top of the silicon on insulator structure, okay, silicon on sapphire, okay. So this we have to talk about, okay. So what is the SOI structure? Okay, we have to talk about the SOI structure. Silicon on insulator, high purity layer on the lower quality substrate, okay. So basically, you must have understood what is the purpose. Okay, the purpose is to grow a particular layer that will contain the specific properties, okay, of our requirement. Similarly, in the CMOS structure, we can do it. Okay, in the same CMOS structure, layers of different doping we can obtain. Okay, similarly, we can like the P layer on the top of the P plus substrate to avoid the latch up. So one of the problem is latch up in the CMOS structure. So yet we have not studied about the latch up. So here you can't understand what is the latch up problem and how this epitaxial layer by controlling its doping profile, how we will be able to avoid the latch up problems. Okay. So here you cannot understood that particular topic, but just for the sake of completeness, you try to remember this point that layers of different doping can be done using the epitaxial method, and that will be used for avoiding the latch-up problems. Okay. Similarly, in the bipolar transistor, we need to produce the buried layers. Okay. I will be discussing the bipolar transistor structure later on in the some other lectures. And similarly, in the 3-5 group 3-5 devices, we can make a different type of heterojunctions. Okay, in that we can make the LEDs, we can make the lasers. Okay, by having the epitaxial layers. Okay, I will take the example. You do not worry. And not in this lecture, but in the, some coming lectures, I will be discussing about these device structures. Okay, there will be able to appreciate how this epitaxial layer is going to help you out and what are their advantages. That time you will be able to understand these advantages of the epitaxial layer. Now, now we have to see another classification of the epitaxy. Okay, as you see in the last classification, I have also written there like type. Here again, I have written types of epitaxy. Okay, so basically, in the last classification, you could have understand that classification was based on the material. Okay, like what is the substrate material and what is the epitaxial layer material. If both are the same, then it is called homoepitaxy. If both are the different, then it is called as the heteroepitaxy. But in the case here, we are actually going to classify the epitaxy based on the uh, type of based on the uh, type of source that we are going to use for depositing the epitaxial layer. Okay, so what we are saying is, so whatever the source that we are going to take to deposit a particular layer, if that source is in the form of vapor, let us say if it is in the form of vapor, and that vapor is going to do a certain, because it is a chemical vapor deposition, as we said, if in the case of gaseous form or vapor form. So if the source is in the vapor form, if it is uh, transported to the reaction chamber and then it is going there and then making a certain reaction and then depositing a particular layer, then it is called as the vapor phase epitaxy. If your source is in the form of liquid, okay, then it is called as the liquid phase epitaxy. Okay, similarly, if it is having in the form of beams, okay, we can take the molecules, or you can take the solid source, and then that solid source will be bombarded by the beams, bombarded by the very high energetic particles at very low temperature, at very high vacuum. Okay, so at very high vacuum, if this is done, then some of the beams of that particular solid material will come out. That will be our molecular beam, and that time it is called as the molecular beam epitaxy. So in the old syllabus, we have to discuss about the vapor phase epitaxy, and then we have to talk about the molecular beam epitaxy. Basically, these two techniques are mostly used. Okay, these two techniques are mostly used. So you can see in the vapor phase epitaxy, what we are saying is material to be deposited will be sent in vapor or gaseous phase. Okay. And then due to a certain chemical reaction, epitaxial layer will grow. Similarly, in the liquid phase epitaxy, it will be sent in the form of liquid, and because of that liquid, maybe this liquid will cool down, and then it will form a particular layer. Okay, in this cases, the thickness control is very bad. Okay, we cannot have the uniform thickness of your epitaxial layer. Okay, but here the control was very excellent. Okay, the control will be very excellent. Either you can grow a very accurate control over the thickness of your epitaxial layer as well as the doping profile. You can accurately control in the molecular epitaxy. So it is one of the most like complex system, though, but it is having excellent properties, molecular beam epitaxy. Fine. So that we have to look at into the details. Fine. So how this method will be used to grow a particular epitaxial layer. So now today we will be discussing about in this lecture the vapor phase epitaxy. So let's begin this one. So in the vapor phase epitaxy, what we have to do is, as I already explained, in the vapor phase epitaxy, what happens? The crystallization, or you can say the grow of the layer, will be taking from the vapor phase, okay, or gaseous phase, and then a certain, due to the certain chemical reaction that will take place, okay, then a particular thickness and doping can also be controlled, okay, and this is generally a very high temperature process, okay, that actually containing temperature like 800 degrees centigrade to 1100 degrees centigrade. It may go up to 1200 degrees centigrade, okay, 1200 degrees centigrade, even 1250 degrees centigrade. So up to that temperature, so it is a very high temperature process, okay, and it is having a very great flexibility, okay, in the fabrication of the devices. So first of all, we have to understand the vapor phase epitaxy process, how this chemical, actually vapor phase epitaxy got the another name, okay. So it is got the, because we are writing here, it is performed by chemical vapor deposition. So basically phase epitaxy is the another name of the chemical vapor deposition, CVD technique. Okay, so first of all, we have to understand what are the various processes onto which, by which this particular epitaxial layer will grow. So that you can understand from this particular picture. So first of all, what we have is we have a particular reaction chamber. Okay, so based on the reaction chamber, whether it is a atmospheric pressure CVD technique, or it is low pressure, or it is a plasma enhanced CVD technique, based on the different type of CVD technique, will have a different properties of this chamber. Okay, so right now let us say if it is a atmospheric pressure CVD technique, so what are the method is, within this chamber what we'll have is, we will be having a graphite susceptor. Okay, so it will be like a base, okay, onto a platform. So it will be giving you a platform onto which we can place our wafers. Okay, so our wafers will be placed over here, and now within this chamber, what we have to do is we have to control the ambient. If it is atmospheric pressure, then we have to keep it at atmospheric pressure. Okay, it should be clean, there should be no contamination within the chamber. And then what we have to do is, first of all, as name suggests, we have vapor phase epitaxy. So while doing the deposition of a particular layer, whatever material we want to grow onto this particular wafer, okay, that material should be sent in the form of vapors or gas. Okay, so that we have to remember, it should be in the gaseous form or it should be in the liquid form within your chamber. So it should be sent in the form of gases. So what we have to do is we have to introduce the gases, okay, into the chamber. Then later on, this particular gases will be actually taken to this wafer surface by the boundary layers. The design of our chamber will be like that. Okay, so you can see that this particular gas stream which is passing like this, some of the gas stream will be taken to this wafer surface. Okay, so now when it is going to the wafer surface, this subsector or this wafer will be heated. There will be a certain heating mechanism. Okay, so based on the heating mechanism, it can be like a cold wall system, cold wall, or it can be a hot wall system. Okay, based on the type of what kind of heating mechanism that we are using. So either it can be a like RF induction heating, or it can be a resistance thermal heating. Okay, or it can be a radiant heating. Okay, So a different type of heating mechanism can be there. So let us say if it is any heating mechanism, okay. So due to the temperature that will be there onto the wafer, what happens is when this reactant gases will reach to the surface of this particular wafer, onto this wafer there will be a certain reaction that is going to take place, okay. And the adsorption of this material, whatever the reactant gases is coming to this particular wafer surface, and due to the temperature when it is doing a particular chemical reaction, a certain products and byproducts will form. So either one gas can be sent within the chamber, or there may be a multiple gases that can be sent within the chamber. So this multiple gases will make a reaction, or if we are sending just a single gas, then it is going to single means it must be a certain source, and that source, if it is sent in the form of gases stream, then it will come to the surfaces, and then it will decompose. Okay, and after decomposing, a particular layer will be formed onto the wafers. Fine. So in that way, what happens is it will make a chemical reaction, then it will be forming a products and a certain byproducts. Then this byproducts must be removed by the gas stream. Okay, so certain layers will be formed, and then this byproducts will be carried away out of this chamber. Okay, it will be carried away by this gas stream, and it will be must be go out of this chamber. So this way our reaction will take place onto the wafers, and then it will be forming a particular layer. One more thing that we have to remember is it is not necessary that whatever the reactant gases that we have introduced and coming to the surfaces are going to react always. It is not necessary. It will completely depend on the sticking coefficient. Okay, so there may be a chances which is called as the re-emission of the reactant gases. So what happens sometimes is whatever gas we have sent has not made any reaction, it will is re-emitted, and it will go out of this chamber without making any layer. That may also possible. So basically it will be depending on the sticking probability of the wafer surface. Okay, so if the streaking probability is very high, obviously certain reaction will take place and it will form a particular layer, and then a certain byproduct will be formed that will have to be carried out. Okay, that should be carried away from this chamber. So this way this entire reaction will take place. Okay, and this way we have to form a particular layer. Obviously you can understand the thickness of the layer, you can say thickness of the layer, or you can also understand you can say the reaction rate. Okay, it will completely depend on the flow rate as well as the temperature that we are using. Okay, what is the temperature of the susceptor of the wafers? Okay, and what is the rate by which the gas stream is actually flown inside the chamber? So both the rate is going to decide the reaction rate as well as the growth rate of the particular layer. As we said that while growing a particular layer, sometimes we also need to dope it. So what we do is we are also sending the dopant gases. Okay, so these dopant gases along with the uh, material source, whatever be the material, if we want to, let us say for example, if we want to grow the silicon layer, okay, monocrystalline silicon layer onto this wafer if we want to grow, then what we have to do is we have to we can use like the selenium gas, we can use the silicon tetrachloride, we can use, okay, we can use dichlorosilane, we can use trichlorosilane. Okay, so these are the different our sources, and this has to be sent in the form of vapors, and along with these vapors we have to also send a certain dopant material in the form of vapors, and that time the reaction will take place, and automatically this dopant material will also get absorbed within this silicon layer, and by controlling the flow rate we can control the doping profile. So these are the different 7 steps that I have explained. Okay, these are the 7 steps that this particular chamber will go through. You can see transport of reactants to the deposition region, transport of reactants from the main gas stream through the boundary layer to the wafer surface, adsorption of the reactants from the wafer surface. Okay, then the surface reaction include chemical decomposition or reaction, surface migration to the attachment sites, kinks and ledges, site incorporation, other surface reactions, emission and redeposition, for example. So desorption of byproducts, transport of byproducts through boundary layers, and transport of byproducts away from the deposition basin. So these are the different steps. These are the basic 7 steps that I have explained. One more point that you have to remember is these reactions sometimes are basically bidirectional. Okay, so we have to keep in mind that these are the chemicals. So when there is a bidirectional reaction, if it is a bidirectional, then we have to keep in mind how to uh, control the various concentrations so that growth of the layer will take place rather than the etching process. You can see, I will explain in the form of chemical reaction. Okay, so I will be explaining through the chemical reaction equation is there. That will be more clear that time. Okay. So one more thing that you have to remember is these chemicals need not to react always onto the wafer surface. Okay, sometimes it may be reacted above the surface. In that time, after making a reaction, it may make particulates. Okay, and that particulates maybe get finally deposited onto this wafer surface. Okay, and those are actually called as the pinholes. Okay, which is not desired actually. Those are called as the pinholes. That we also keep in mind. So now based on the different, I'll just explain you a more detailed structure of these type of systems. Okay, so just you see, this is our atmospheric pressure CVD reaction chamber. Okay, in this chamber you can see we are having a graphite susceptor. Okay, you can see this susceptor is actually having a little tilt. You can find out. Okay, not perfectly horizontal, but it is having a little tilt you can find. Okay, then you can see we are having the RF induction heating coils we are having here. So when it is a RF induction heating coil, only this susceptor in this wafer is going to be heated. Okay, this entire body, entire chamber wall is not going to be heated when it is a RF induction heating. Fine. So you can see in this we are having a particular gaseous sources, like you can see, first of all, let us say we want to grow the silicon layer onto this particular wafers. Okay, then we have to think about which particular source we are going to use. So this source can either be in the form of gaseous form. Okay, if it is available. If it is not available in the gaseous form, then we can also take the liquid sources. For example, SiCl4, our silicon tetrachloride, will be available in the form of liquid. Okay, so we can also take the liquid source. Similarly, uh, other gases that we want for reaction purposes, that need to be sent in the form of gases. If it is not available in the form of gases, then obviously we can take the liquid source, but along with the hydrogen gas or some other gases like argon or nitrogen. Okay, so that time this hydrogen, like in this case, you can see this liquid cannot be sent to the reaction chamber. Okay, so what we do is we will be sending the hydrogen gas. So this hydrogen gas will do the bubbling, and that time it will be carrying the vapors of the silicon tetrachloride to the chamber. So basically it is acting like a carrier. Okay, or hydrogen gas will be acting like a carrier over here. Fine. Similarly, this hydrogen gas can also be used for any other liquid sources. Okay, and then we can also use nitrogen gas or argon gas for that purpose. So here you can see we are sending the hydrogen gas, we are sending the argon gases. Okay, so these are the carriers. Okay, these are the carriers for those particular sources which is not available in the form of gases, but rather it is available in the form of liquid. Okay, so here you can see we are having this B2H6. We are having, this is our phosphine gas. It is B2H6 is basically for your doping purpose. Okay, in which we have to do the boron doping. Here we have to use the phosphorus doping. Okay, so it will be available, must be in the form of gas. So this will be must be sent through uh, with the hydrogen gas. Okay, so these are the doping sources. Okay, and another HCl source is available to get a particular chemical reaction. Okay, so these are the different valves, and these valves will be opened properly, and then it will be sent to control the flow rate of these all reactant gases. Okay, these gases will be sent to this reaction chamber, and you can see when this gases is going like this. Okay, when it is going like this, okay, some of them is going to be make a reaction at the wafer surface. Okay, so just to have the same flow rate for all the wafers, we need to tilt it a little bit. Okay, because here when some of the gases is going to be absorbed, okay, that time the amount of, if it is we keep it horizontal, that time this first wafer is going to be exposed with the more amount of reactant gases rather than by the last one. Okay, it will be having the least amount of gas will be reaching up to this particular thing. Okay, and it will be getting less exposed, so that time the growth rate will not be same. Okay, so that's why what we are doing is we are tilting it a little bit so that the gases will be coming like this, and the gases which are not reacting onto the surface of the first wafer may also reach to the second one, and those gases are actually not reaching to, not reacting with this and flowing just, so obviously it will be forming a different layers while flowing. So these gases is directly go to this, and then it will be making a reaction with particular wafers. So this type of arrangement we have to make, and then the reaction will take place within this chamber, and due to the reaction material will get deposited, and the other byproducts will be taken away through this particular vent. So you can see, because we are saying that it is RF induction heating, the only graphite in the susceptor will be heated. So it is called as the cold wall system. You can see we are writing here, it is the atmospheric cold wall system. Okay. So because this entire chamber is not heated, okay, these walls are not heated. Okay, you can see in the another system we are having a low pressure hot wall system. So what we mean to say here hot wall system, because here all the wafers are kept vertically. Okay, it is kept like this, it is a kept in this particular cassettes, okay, a particular wafer holders. Okay, and within this wafer holders we have to send the gases. Okay, and in this particular arrangement the heating will be done with the help of resistance heater. Okay, so when the resistance heating will be used, this entire tube is going to be heated. Okay, this entire tube will be going to be heated, and whatever inside this tube, everything is going to be heated. Okay, and that's why we are calling it as a hot wall system. Okay, it is called as the hot wall system. So in this case, we have to send the gases again, and this gas will go inside, and because of the hot wall system, some of the reaction also take place at the side walls also, and some of the layers may also get deposited onto the side wall. Okay, and basically this system is actually used for deposition of the polycrystalline amorphous films. Okay, these are the like silicon dioxide if you want to grow. Okay, so then we have to go for such systems. Fine. Now you can see in the commercial cases we are having this type of reactors also. You may find that pancake reactor, you may find, in which the arrangement is a little different. Like in this case, if we are having RF induction heating, then we will be having here the heating mechanism. Okay, it may be a resistance heating, whatever it may be. So if some heating mechanisms will be there, the gases will come from this side. Okay, as you can say, we have to tilt the susceptor a little bit. In this case here, what we have to do is we have a particular susceptor in this fashion, and this particular uh, the vent through which the gas, or you can say the inlet, okay, through which the gas can enter, it will be centrally mounted. Okay, and we have a disc shaped susceptor, and this onto this disc shaped susceptor we can place the wafers, okay, onto that particular disc shaped susceptor. and then the gas will go like this, and then again it will be carried to this particular wafer surface by the side walls, okay, boundary layers, and then it will come, then it will make the reaction, and then it will be coming out through this particular way. Similarly, this is called as the pancake reactor, and in this case again it is having a barrel reactor. Okay, these are the most commercially used, and in the barrel reactor we are just using the radiant heating mechanism rather than the RF induction heating or resistance heating. We are using the radiant heating. Okay, so radiant heating mechanism will be used. So these type of different arrangements can be used for our epitaxial layer growth. So now we can look at the various chemical reactions. Okay, as I already explained that these chemical reactions will take place, it may be bidirectional. For example, if we want to grow the silicon epitaxial layer, okay, then to grow the silicon epitaxial layer, the various sources is like silicon tetrachloride. You can either use SiCl4, and the reaction temperature may be 1200 degrees centigrade, more than 1200 degrees centigrade. Okay, so what we have to do is we have to send the SiCl4 vapors, plus we have to send the hydrogen gas. Okay? So because hydrogen gas will be carrying this particular thing. So after making a particular reaction at this particular temperature, it will be forming a silicon solid layer. Okay, and then this is the byproduct 4HCl that will be formed. Okay, that has to be carried away. Okay, and as I said, it is a bidirectional reaction. Okay, so bidirectional reaction, then obviously you can see another product that can be formed is this. Okay, SiCl4 gas which is coming, and then we have already made a silicon layer. So this silicon layer is going to be make the reaction, and then again it will be forming this particular gas SiCl2. Okay, so again, because in both the cases it is a bidirectional equation. So what does it mean? This silicon can again react with the 4HCl and again make the same thing. Okay, again make this particular thing. So that we need to take care that, because it is a bidirectional reaction. Okay, so there may be a chances that either a growth can take place, or there may be a chances that the silicon layer may be etched out. Okay, that we have to keep in mind. So that has to be controlled by controlling the concentration of the SiCl4. Lots of investigation has been made, and then they have found at what concentration of the SiCl4 should be sent within the chamber, so that only the growth can take place. There should be no aging. Okay, so another reaction you can find is trichlorosilane. Okay, SiHCl3. Okay, so this will be the chemical reactions. Again, all the reactions are actually your bidirectional reactions. Fine. And finally, we can deposit a silicon layer. Either any sources can be used. Fine, any sources can be used. But if you want to have a low temperature process, then obviously you can go for dichlorosilane or silane gases. Okay, if you want a low temperature process. Fine. If you want a high temperature process, you can go for this particular sources. Now you can see the effect of this silicon tetrachloride concentration on silicon epitaxial growth. Fine. So you can see if we are able to control the mole fraction, okay, mole fraction of SiCl4 within the chamber, such that if it is low value, okay, you can see we are having this mole fraction of your silicon tetrachloride. Okay, when this value is very small, like 0.05, 0.1, okay, then initially this film growth rate, okay, so micrometer thickness, okay, so micro to grow the micrometer thickness per minute, okay, this rate will initially increase, okay, when we have a very small fraction of our silicon tetrachloride gases into the reaction chamber, okay, very small fraction, and when we increase it a little bit, okay, so it will be start increasing slowly, and it will reach to a maximum value. Okay, so growth rate will be maximum at this point. And when we further increase the growth rate, okay, we further increase the concentration of your silicon tetrachloride, then this particular growth rate will start decreasing. Okay, so what it reflects, it will keep on decreasing, 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 and then at a particular concentration, when it is becoming sufficiently high, okay, at that time you can see this actually going to be in the negative direction. Okay, so in the negative direction, it reflects that rather than the growing process, the film is not grow, but rather it will going to etch out the silicon layer. Okay, so after this particular concentration, the etching of the silicon layer going to be take place. So that we have to keep in mind that the concentration of silicon tetrachloride should be controlled such that the growth of the film should be take place rather than the etching. Okay, so I hope this must be clear. So we will be having another discussion on the vapor phase epitaxy is already over. So we can discuss about the molecular beam epitaxy in the coming lectures. So thank you for watching.